Anyways, my name is Ben Names. I'm a senior aerospace stress engineer here at SDA, Structural Design Analysis. We just always shorten it to SDA. And today I'm going to be talking about aeroelastic analysis for full aircraft. Really quickly, let me just see if we still have people rolling in before we get going too far. Okay, we still have a few people rolling in, so I'm going to take a little bit longer than I normally would on this intro. Anyway, so we're talking about aeroelastic analysis for full aircraft. And, you know, in general, the physics are exactly the same when it comes to if you're talking about a full aircraft or, you know, part of one, a substructure like a wing or a nacelle or a canard. Again, all the dominant physics is there, but there are some subtleties that end up coming up that you typically encounter much more frequently when talking about full aircraft. All right, so I'm going to just go ahead and jump in then. So just to give you guys an idea for where we're going, what we're going to talk about, I'm just going to, for those who don't know who we are and what we do, give a brief overview about SDA. Then I'm going to talk about some of the specifics about setting up your model. And again, we've already gone over the kind of introductory setting up models and stuff like that for aeroelastic analysis in a previous webinar. So if you haven't seen that, go to our website after this, and it walks you through how to set up, you know, simple aeroelastic static and Flutter analysis for a single wing. But today I'm going to get into a little bit more of the subtleties involved with, again, setting it up for a full aircraft, what some of the differences are. And then I'm going to run through a static aeroelastic trim analysis example and a Flutter analysis example for a full aircraft. In fact, the one that you see below on the model. I'm here over kind of what we're going to tackle today. And then we'll have a few conclusions, etc. So without further ado, here at SDA, we're a team of about 14 engineers. We do primarily structural analysis on aircraft and spacecraft, although we dabble in a few other areas when it comes up. We specialize in composites, lightweight structures, and we're very fluent in a whole slew of different analysis software packages. And in fact, we actually end up reselling a lot of that software too. So not only are we good at using it, we're good at teaching how to use it. At the very bottom of your screen, you can see a bunch of the different, or just a few, of the customers that we've supported over the years. Actually, today, I'm going to highlight a model that we created while conducting some stress analysis for vanilla aircraft. So without further ado, I want to present to you all Vanilla Aircraft's VA01. It's a HAIL aircraft, and again, in that class of aircraft, you know, high altitude, long endurance, typically you end up having long slender wings to get, you know, your highest aerodynamic efficiencies. But what that often translates to is higher flexibility, and really the aircraft tends to be more susceptible to aeroelastic effects like Flutter and that kind of a thing. Now, before we dive too much into the model, I want to go over just some preliminaries, make sure we're all on the same page. Again, if you're looking for some more introductory explanations, go back to our kind of intro to aeroelasticity webinar that we had roughly 6 months ago. You can find it on our website. But it is important to kind of make sure that we're all coming onto this from roughly the same footing from a high-level perspective. So static aeroelasticity talks about, it really is concerned with two main sources of forces. You have your aeroelastic forces, that's represented by your stiffness matrix, right, that K matrix, and then your aerodynamic forces. And those come into play into two senses. And I'll get into that in a second. Again, this analysis is linear. There are instances where you can do nonlinear aeroelasticity, but Nastran really focuses on just the linear aspects of that. The general procedure for what's going on under the hood with Nastran is you supply, some structural model as well as an aerodynamic model, and what it's doing is it'll first calculate the rigid aerodynamic influence coefficients. Okay. Once that's done, it'll go in and kind of determine what I want to call a modified stiffness matrix in an aerodynamic modified stiffness matrix. Those of you who are familiar with buckling analysis, it's kind of like your geometric stiffness matrix. This is going to add to your just traditional stiffness matrix, and again, often like buckling, this will soften your structure in a lot of places due to aerodynamic forces. And then again, it also calculates the rigid forces due to your aerodynamic model. So this should give you all a rough idea as to what's going on under the hood. Now, one of the really important things that comes up when considering full aircraft is, so take this picture on the right. It's a really silly image I drew up, but say we have some conventional aircraft. At cruise, we'll probably want some positive angle of attack on our main wing so that we're generating enough lift to fly, right? And then simultaneously, we know that we have to provide some downward force from our tail, which means it should have some negative angle of attack. However, when you create these panels in Nastran, and in fact, I'm just going to pull up my model really quickly. We might as well. So here's that model, this beautiful model we have. I'm going to hide the structural model really quickly. We're just going to look at the aerodynamic model. And if we look at this, you'll notice that none of my panels are angled up at all. All of them are flat, running parallel with the stream in the streamwise direction. Okay, and this is really important. The way that we add those kind of effects that we want to consider, like an initial incidence for our wing and initial negative incidence for our tail, is we add downwash in and modify the downwash at any boxes that we need, right? This is effectively the same thing as just adding a local angle of attack for those surfaces, okay? And again, it gets pretty complicated, so I don't want to spend too much time on this, and if anyone has any questions, I'm happy to answer them at the end of the webinar about this. But roughly, you do this with a DMI input statement, direct matrix input, and you're essentially writing information to your to the W to GJ matrix. Again, you don't have to worry about it too much, but there are a few things you need to know when writing a statement like this in your bulk data entry. So the first thing, you have to know the number of panels you have in your model. That's M. If you're running a static aeroelastic analysis, you have to know the number of trim cases you're running, okay? And then as you're modifying your boxes, you modify them for each trim case, all right? Now, often if you're modeling a geometric kind of downwash, right, a geometric angle of attack, we'll do that the same for every trim case, but you do it on a per trim case basis. It's important right here, notice on the second DMI input line, this is again, I'm calling out what trim case I'm modifying. This first box states that I'm modifying the downwash, or I'm applying some initial downwash at box 1. What that downwash is, this is in radians, so this is actually a positive downwash of 1 degree. And then the last box that I'm going to be modifying in that series. And we can do this for as many boxes as we want. One thing that's really important to note when you're setting up this model, I'm going to go ahead and just hide everything but our first box. Let's see. All right. So if we zoom in on just one of our panels, you're going to notice that the panel ID, the number starts at 1, and the next one starts at 601. Okay, so why is that? Well, if I go ahead and, let's see, there we go. If I go ahead and show all of the elements in that arrow panel, you'll notice it starts at 1, it runs chord-wise, and as we go to the span then, the very last box is box 600, okay? So you are, in fact, when you make one of these panels, making a series of aero elements, okay? And it's important to note that you don't want to, you can't renumber your next panel or start your next panel numbering, right, such that it would start overwriting your other panels. Now, again, or other panel elements. Now, I only go into this detail because it's important to note, for example, again, I'm going from 601 to 1200. It's important to note when I'm making one of these DMI inputs, right, which boxes I'm modifying. Okay, so anyways, this is just to give some perspective on some of the intricacies involved in modifying that those arrow boxes. Now, another intricacy that comes up is we actually have to start paying attention to the element normals of the arrow elements. Okay, so let's say we make an arrow panel like this, and we number the inboardmost point 1 and 2, okay, and the outboardmost points 4 and 3, right? Pretty standard, nothing too fancy. If you use a right-hand rule kind of configuration and go 1, 2, 3, 4, you'll notice that the element normals are pointing in the positive z direction, okay? So if we want to, and you can see kind of a cross-sectional cut below that guy, if we want to modify the angle of attack, the geometric angle of attack of one of these panels, effectively what we do is we add a vertical downwash, right? Okay, so we're adding some positive downwash. It's positive, consistent with my element normal. And that means that we have some increased angle of attack that's essentially effectively modeling our geometric angle of attack, okay? Now, suppose that we have a different orientation. What if we have our wing actually running in the negative y direction, okay? We're still numbering our panels, 1, 2, 3, 4, 1 and 2 being the inboardmost, 4 and 3 being the outboardmost. If you use that right-hand rule again, you'll notice that the element normals now for each arrow element are pointing in the minus z direction, right? So what does that mean? If I want to add that downwash, I need to add it to that box as a negative downwash instead, okay? Which would, again, effectively increase the angle of attack locally of that panel, all right? So again, generally speaking, these kind of effects won't come up too much, but if you start modifying the aerodynamic model manually this way, you do need to be aware of these kind of subtleties. So here's a perfect example of that. We have our model. I ran a static aeroelastic trim. I think it was a steady level flight, okay. The right and the left wing in this case use different element normals, and I'm applying no downwash, okay? So if you look, I drew the displacement on the right-hand side, the right wingtip and the left wingtip. It's the exact same arrow, just copied and pasted, so just kind of a vector representation of my displacement at that point. And they are, like we would expect, exactly the same, okay? And this makes sense. It doesn't matter from a numerical perspective what that element normal is, because Nastran will know to solve the singularity strength of that element and figure it all out. You don't have to worry about that. However, when we start modifying, right, if we want to apply some initial downwash, effectively increase the angle of attack of our wing, those effects come into play. So on the left wingtip, you see I just drew that same arrow where we have a higher displacement, right? That arrow doesn't quite reach our wingtip. We have a higher displacement, which makes sense because we effectively increased our angle of attack. Now, what happened on the other side? Well, I had a negative element normal, which meant that when I added a downwash, it actually reduced the angle of attack because I used the same positive downwash over the whole span of the wing. So again, these are details that will not always come up, but if you start modifying the aerodynamic model, you kind of have to be aware of them. And often you can kind of get through these with some just kind of sanity checks by running some comparisons, adding a positive downwash, negative downwash, checking the results. But it's important to be aware of these kind of problems. Next is something much more simple, so you can relax for a second. I know that was pretty intense. Setting up control surfaces is relatively straightforward. there are only a few things you really need to enter. The first being you need to enter a title and a label. It's important to label these consistent with certain keywords that Nastran uses. For example, for an elevator, again, it's elev, like that. I'm going to pop out real fast and show you. Let's see. Let's go hide those guys, and I'll just turn everything on really quickly so we can see it. Let's see, just show all. And we're going to look at our control surfaces. Okay, so we also have a rudder control surface in this case, although we don't end up using it. But the keyword for using a rudder is just like it's spelled out right there. Okay, so again, these keywords are listed in the QRG and in the Aero PDF help file. So if you want to know more about those, you can check them out. But again, that's what these are. In terms of adding these parameters, a reference chord length and a reference surface area, these are really just important if you want to recover your hinge moment coefficient. So if that's not something you need to know, don't worry about it. You can leave them blank. Last but not least, I'm going to just pull up the PowerPoint because it's a little bit clearer for now. You have to list your hinge orientation coordinate system. That's this coordinate system I have listed right here. If you'll notice, the Y axis of this coordinate system points along the hinge line. That's how it's defined. You can look it up in the QRG. And then if you click this arrow mesh, in fact, let me just do it right now so I can show you. So we're looking at this. Let's say we wanted to add to our elevator. Sure. Edit this guy. We go into our arrow mesh, and now we can manually select more boxes as we go along. Okay. Anyways, so that's setting that up. It's relatively straightforward, but again, something that comes up a little bit more often when dealing with full aircraft as opposed to just a wing. And finally, the last bit, well, the last thing we have to worry about is setting up our coordinates or our constraints correctly. When we're running a trim analysis, we need to release certain rigid body degrees of freedom so that Nastran can go in and figure out, using the variables that we've given it, how to set those equal to 0. Okay, so in this case, we're going to consider two different flight cases, really, a step-up flight, okay, and a 4G pull-up. And in essence, those are actually almost identical. The only difference is in the 4G pull-up, we're accelerating in the positive Z direction by 4Gs. So anyways, so we want to physically constrain degrees of freedom 1, 2, 4, and 6. Okay, so you can see that kind of here. And then we want to use a support constraint for the pitching and plunging degrees of freedom of our aircraft using a support card. And you set that up the same way. For those who aren't familiar, it really is just like setting up another constraint. If you can see here, it's just listed like another constraint. If I edit it, you can see I've constrained TZ and RY. So again, relatively straightforward. And with that, I think actually we can jump in and start talking about how to actually set up one of these analyses. So you can see I have a steady level flight analysis. If we go ahead and edit it, it's at 65 miles an hour, so it's roughly the stall speed, a little bit above, roughly the stall speed of the aircraft. We're running a static aeroelastic analysis. If we go into the manual bulk data, I have some fuel mass here, but you can also see I actually have that modified downwash section in here. For now, I haven't actually added any incidents. I'm just letting that for this is for the wing, okay? Boxes 1 through 5,250, not modifying that, but that's the wing. And then this part here is for the tail. Haven't modified those, but we could go ahead and add that if we wanted. Again, skipping through, this is exactly the same as when you're running it for like a wing, so I'm not going to spend any time on that. Finally, this is where it gets a little bit different. So we enable our trim analysis. We set our dynamic pressure. And then we have certain variables, okay, that we can use to trim our aircraft. The variables that we essentially are giving it are the angle of attack of our whole aircraft and the deflection angle of our elevator, okay? So those two pieces of information will be enough to restrain it in that pitching and plunging orientations, or in those pitching and plunging degrees of freedom. We also have to set our pitch rate and our pitch acceleration to 0 to make sure that we've kind of isolated that it's also not accelerating or rotating in the pitching degree or pitching direction. And then in order to kind of state that we're flying at in a steady level flight maneuver, so to speak, we'll just set 1 for a 1G acceleration, okay? But if we wanted to, we could go ahead and, of course, manually edit this to 4, and now we're doing a 4G pull-up, all right? So that's really all that there is to say about that. And again, finally, we have some constraints here. We have some supports, and that's it. And just so you all know, it outputs all of the same information. I'll show it for a second briefly, but it outputs all the same information that you would get from a static analysis, okay, a linear static analysis. So if we go down here, I'm just going to, let's see, let's go ahead and look at the 4G pull-up case, turn on our FEM, because it's kind of hard to see without that. And voila. So this is like a sample of what that output might look like. And we can turn on our deflection, and we can roughly see what's going on there. Currently, we're looking at laminate max failure index. Again, this is kind of a manufacturer just problem example that I did on this model, but it gives you a really good idea as to how we could, without having to know any have any knowledge about what the loads actually are, we know just very simply that our aircraft might be sized by a 4G pull-up case, for example. You can do banking and coordinated turns too, but you can set this information at a really high level and then really allow Nastran to disseminate that information and spit out some really detailed loads and then, of course, stresses and strains on your model. So from a structures perspective, you get to cut out a lot of the middlemen in terms of not having to worry about accurately calculating your loads. How different is your aerodynamic, are your aerodynamic pressures compared to what they would actually be if we ran CFD or another panel method? You don't have to worry about that. It really calculates all that internally. So again, it provides you displacement, stresses, strains, element forces, etc. All that internally. It also calculates accurate aero panel distributions. And it trims your aircraft so it can tell us what our trim variables should be. In this case, it was our angle of attack and elevator deflection. And then finally, if you're interested, it also gives non-dimensional stability derivatives. So we are running a little short on time. I spent a little bit longer on that than I wanted. But I want to go over some of that. So if we open up the F06, this is where a lot of that information is kept. Okay? So if you look, we have, let's see. So if we look at our load factor, our vertical acceleration, again, you see this is for a steady level flight case. In this case, Nastran solved that we needed this many radians of angle of attack and this many radians of negative deflection, okay? So if we translate that into degrees, which we all understand, this means we have angle of attack of about 7 degrees and an elevator angle of about -4 degrees, okay? So these are relatively reasonable deflections that I don't think would surprise too many people. And it's great that we were able to get this information, again, providing very high-level numbers and then allowing Nastran to kind of dig through the dirty work. All right. Now for some other cool stuff, let's talk about Flutter analysis. Unlike static aeroelasticity, when we talk about Flutter, we need to also include the inertial forces within the structure. So most of you probably know this as your mass matrix, that M matrix. Again, the process is generally, you go ahead and conduct your normal modes analysis. You calculate your AIC matrices for every combination of Mach number and reduced frequency, and then you iteratively solve an eigenvalue problem for each mode at each unique dynamic pressure, effectively, or airspeed, really. So you solve those problems and you get your frequency and damping of each mode progressively. Okay. Now, again, there aren't too many differences between doing a full wing, or doing a wing and doing a full structure. But often with a wing, you don't have to consider the rigid body motion since you don't really have enough fidelity to consider them. So, many fewer modes that you have to consider, which is nice. Interactions between, for example, a wing and a tail or a wing and a fuselage aren't considered, so you are making some assumptions about that, but it simplifies the model greatly. When we're talking about a full aircraft, we honest to goodness really have to consider up 20 to 30 modes, sometimes more, depending on the aircraft in general. And we do have to consider a coupling between the rigid body motions and the elastic motions of the structure. On the right-hand side, I just took this as a GIF we've used a few times, but this is a project that the AFRL has spent a good deal of time and research towards. It's a flying wing, but it was designed such that it exhibited body freedom flutter at a particular airspeed, and then the whole point of the project was really focused on using control systems to reduce that effect. We're not going to get into the control systems today. That's not our specialty, but we will talk about body freedom flutter towards the end. So if we jump back out to our model, one last thing I want to mention really quickly. When we're running a flutter analysis on our model, again, it's actually set up almost exactly the same way. I'll jump in and we can maybe run through it at the end if someone's confused about something. But one of the differences is this is actually completely unsupported. There are no constraints on this model, and that's how you want it to be, because you want to be able to consider the rigid body motion. So if we go in, and let me just run to the boundary conditions, you can see we have no constraints applied to the model. This is what we would expect. We need to be general and not assuming that those rigid body motions don't affect the vehicle. So we can see this is just a frequency versus airspeed plot. You can see the modes kind of moving around. It might give some indication as to which modes are being coupled with others. These are all of the relevant ones. You see, in this case, I only ran 25 and down selected a few of those that were a little bit distracting. But one of the things that is interesting, most people might catch, is this mode 7 down here. That's the first wing symmetrical bending mode. And you can see it does become critically damped for a small series of points, and then that frequency curve pops back up. And so often what that kind of falling to a zero frequency, becoming critically damped, means is you need to look out for divergence. In this case, it's not too much of an issue, but it is something that you need to be able to consider. You might want to watch out for. If we go to our damping, we can see our damping versus airspeed. That the mode that actually went unstable in this case is this mode 21. Okay, and let's see. Let's go to another plot. This is where it's all cleaned up. So these are the 3 modes that go unstable. This is mode 21. That we also have mode 13 and 25 that go unstable. Okay, the flutter speed is 310 miles an hour, which is pretty high. You're starting to get into that compressible region, which is okay, and we can model that, but likely for a HAL aircraft in its performance, it won't be encountering that. So this is good. This means that this aircraft was well designed, which is great because we had a big hand in doing that. So this is something we like to see. Now, going more specifically, let's take a look at what that flutter mode looks like. So this is kind of a crazy flutter mode, and I'll go into Femap in a second, but let's just take a look at what's going on. So you can see we have an anti-symmetric bending mode, first bending mode, coupling with it looks like some torsional behavior in the wing, and then there's also some bending that's being contributed at the tail. And one thing that I found fascinating, if anyone has seen the old NASA kind of introductory video about Flutter, it's got some really goofy music. In our article, I mentioned it as just an example of kind of some of those interactions that you can get between the wing and the tail and the entire aircraft. But what I thought was really funny is if we compare the flutter mode of one of those aircraft in that video, you see it looks a lot like the Flutter mode that we're exhibiting, which makes sense. They're very similar aircraft. They have very similar layouts. It's no mistake that we're seeing such a similar Flutter mode between these two. And as you can see, this is live footage, so this was recorded by NASA a while ago. Anyways, let's jump in. I also want to show one other thing that I didn't mention in the last video, in our last webinar. Let's see, we're going to go ahead. I want to just animate what these different Flutter modes look like. So that was the 21st we saw. Let's animate one of the other ones. Let's animate this guy. And I'm going to turn off our aerodynamic model. So you can see this is much more of a, almost looks like a galloping Flutter mode, and it is the less critical one. If we look at the plot, the damping plot, the damping approaches a positive value a little bit more slowly, so likely this one we have to worry about a little bit less. Finally, if we look at the mode 25, we see that actually this looks a lot like that mode 13, and we have some strange behavior going on, likely with how some mass is attached to rigid body elements down here. So we can probably neglect this really as a Flutter mode, knowing that it looks like there's some strange modeling effects that are going on. And so we can probably safely ignore this guy. Now, let's see, we still have time. I do want to mention this because it is very important. When you request your Flutter modes from Nastran, it actually outputs the mode shapes in this format to Femap. Okay, so this is how it'll come in. It shows you what the damping is. One of the things I forgot to mention is how to actually convert that into something where you can see the out-of-phase interaction between modes. Okay, so let's say we let's take a look at, this is our, I believe, okay, so this is our first unstable Flutter mode. Now, I'm going to pause that animation. If I want to expand this so I can see an accurate representation of what this mode really looks like and we can see stuff going in and out of phase with each other, you want to go to Model, Output, and then Expand Complex. You can either select the mode shape that you want, or if you already have it active, Femap will auto-select it for you. In fact, I think if we can see Femap has already selected that for us. You hit OK. And then all you need to do is give it a range of phases to kind of go through. So in this case, I'm going from 0 to 360 degrees. And we could, usually I choose 15 as the number of degrees to kind of increment, but you could do any number. And then that will output as results, and you can put them in an analysis study and then animate the study. Okay, so that's how you go about doing that. Now let's talk, as we're just about to run out of time, we have a few more minutes, let's talk about body freedom flutter, because I did promise that, and it's a very cool effect. So what I effectively did, actually, let me jump into the model. I know, sorry, that was a little scatterbrained. Let's jump into the model, and actually had to tweak it because, as you saw, we don't see body freedom flutter in this analysis, right? Our model didn't give us that. So in order to make sure that you guys could see that, I went in and I tweaked our model a little bit. And effectively what I did is I increased the mass weight parameter. So really what this is, I'll give you just the numerical representation, is 20 over 386.09. So normally you put 1 over g in this case to be consistent with your units. So effectively what I've done is I've scaled the mass up by 20 times, okay? So what was I trying to accomplish by this? Well, one indication that you have body freedom, that you might encounter body freedom flutter effects, is if your first vertical bending frequency starts roughly at about anywhere between 0 and 2 hertz, okay? So if we go back to our original frequency plots, you'll notice unmodified, our first bending frequency is about 5 hertz, okay? And so in order to get the behavior that we want, scale the mass by about 20 times, and now our first bending frequency is actually at, what, about 1.2, 1.25 hertz, okay? And so by doing this, we changed, by adding that mass, we reduced the frequency, and we did end up getting body freedom flutter. Okay, so these are what our frequencies look like. These are what I thought the important frequencies were to look at. We can see this is the damping, and again, it's clear that actually this mode 6, which again, mode 6, all of you should know, 1 through 6 should be the first rigid body motions, right? Rigid body mode shapes, motion mode shapes. Mode 6 goes unstable, right? So, okay, let's look into that. Let's see what's going on. And if we see, I've kind of plotted what that behavior looks like, starting at 73 miles an hour, then 150, then 220, where it finally goes unstable. And we can see even by 150 miles an hour, that pitching, plunging kind of motion, more the plunging motion, and the first bending motion of our aircraft have coupled pretty substantially, actually. And if we look, although for 73 and 150 miles an hour, they look relatively in phase. If we look at the 220 mile an hour airspeed where it finally goes unstable, you can kind of see that the plunging motion of our aircraft coupled with the first bending mode is actually out of phase with each other, okay? Now with that being said, just as a quick shout out, that kind of wraps up the big topics, the aeroelasticity topics of our webinar. We are offering a training later this month, and we offer trainings periodically. This is just for kind of basic Femap with NX Nastran training for those who need introductory courses, but we do offer a whole series of them. So if you're interested in training, please feel free to get in touch with us over that. That is something we offer. And in fact, 2 other things that I want to mention. Not only can you hire us to do your aeroelastic analysis for you, it is a pretty focused, pretty deep field in and of itself, and fairly specialized. So if you don't want to have to go and learn some of these intricacies, we can do it for you, no problem. We have a lot of experience doing it, and a lot of resources with which to draw upon. And then finally, we're actually, if you do want to run your own aeroelastic analysis, we're running a 10% discount through March 31st. So if you're interested in that, contact Marty Civic. He's our sales guy. He's wonderful. He's a great guy to talk to. There's his email, and in fact, if we go to the next slide, here is both of our contact information. So let's go ahead and open it up for questions. I know this was a fairly long webinar, but again, a lot of the topic, a lot of the subject matter does get pretty specialized and pretty deep at times. So I wanted to make sure that we spent enough time on all of that stuff. Let's go ahead and answer some questions. Let's see. Oh, no questions yet. Oh, and I'm so sorry, I forgot to mention we are running a poll, so you can go ahead and answer that while we start answering questions as they come in. Oh. Let's see. We do have questions. Oh, this guy. Oh, sorry guys. I had to have my my friend Ashwin help me out. Okay, let's see. So we have some questions while you're filling out that survey. Oh, that's not what I wanted to do. Apologies. Try one more time. Okay. All right. Where is the Intro to Aeroelasticity webinar? If you go to our website, let me see if I can just, let's see, I might be able to do this on the fly. If we go to Structures.Aero, so if you go to our website, hopefully this this will go okay. There is a webinars tab that you can look at, and that's actually where it's where our webinars are posted. I'm going to let that run in the background. Let me look at the next question. In which unit Femap imported the geometry will follow? Okay, yeah, so it looks like Ashwin already answered that. Femap and Nastran are unit neutral. so you do need to track your own units. That's why, for example, I was dividing by 1G in inches in the inch-based unit, because we wanted to make sure that although I had pounds represented in the model for the mass, we need to convert it to an actual true mass. Let's see. Damping. Okay, interesting. Yeah, so this is aerodynamic damping. This is not structural damping. That's a really great question. Often you can consider the structural damping, unless you really want to get into the nitty-gritty. The structural damping can be introduced as just a proportional, say 1%, usually anything reasonable is between 1 and 5% proportional of your stiffness matrix. If you want to get a little bit deeper into that, you can, but you do not always need to. Often that gets pretty deep. Oh, let's see. Yes, good card, good call. Let's see, I'm going to go to some of the more recent, and then we'll backtrack a little. Do you recommend performing divergence predictions using static aeroelastic solution and a divergence card? You absolutely can. Put it this way, if you want to pick up a divergence eigenvalue, you're guaranteed to get it if you use the static aeroelastic solution using a divergence card like that. You can also pick it up while doing a flutter analysis, but of course you're not guaranteed to get it if your aircraft doesn't happen to diverge in the airspeed range that you supply. Does the number of velocity points in a flutter analysis help the mode tracker? Yeah, absolutely. Again, one point I should actually mention. In theory, that would work. Nastran, at least for the basic Flutter analysis, does not actually support mode tracking. It does in Solution 200. It does not in Aeroelasticity, from the best that I can tell. But if it did, then yes, of course, supplying closer velocity steps would help it to do the mode tracking. The way it really does it when it spits it out is it just sorts it by frequency. So that's often one of the better ways to tell if you do have mode switching. Let's see, there are a lot of questions, so I'm going to try and run through it as well as I, oops, let's see. Okay. So the most recent one came in, so the T46 Flutter report recommends performing Flutter runs with a range of control surface moment deflection effectiveness values. Does this mean Nastran provides a means for varying that effectiveness? Yes, it does, yeah. So I mentioned supplying the DMI input for initial downwashes. You can also actually supply initial effectiveness for changes for not only the, so you can do it within the control surface the way I showed with that control surface effectiveness. Let me see if I can pop that up really quickly. So if we go into control surfaces, I edit one of these guys, you can see that we can put what effectiveness we want that control surface to be at in terms of how it transmits that force. You can also manually modify the strength of those singularities in the same way that you supply kind of an initial downwash. You can also use the DMI statement in the bulk data entry to manually edit the strength of what those singularities should be. So you can knock it down by 50% or 80%, whatever you think, so you can range over you can sweep over a range of frequencies. That way you're considering that kind of behavior, because that is important when you're talking about control surface flutter. So thank you, Sam, for mentioning that. Let's see. I have not ventured too much into control surface reversal, but again, you can absolutely just do that with static aeroelasticity. If you want to talk about buffeting and more kind of really dynamic aeroelastic behavior, that's not currently supported by Femap. So that is something to keep in mind. Yeah, and you know what, it looks like at this point it's probably time to wrap it up as we're pushing about 15 minutes. All of these questions are saved for us, and if you have any more questions, again, let me just throw up my contact information and Marty's. So if you're interested in sales, definitely contact Marty. Again, he's a great guy. If you're interested in talking more about some of those solutions, feel free to contact me. Here's my contact information. And this presentation will be posted on our website as well in the next day or so, along with, I think, the slides. So anyways, I want to thank everyone so much. I hope this was informative. I hope that you learned something if you took the time to watch. And again, if we can help in any way, whether providing the software selling or services about actually conducting that analysis ourselves, we're happy to help out in any way we can. So thank you so much, and I hope everyone has a great day.